Good evening, everyone. So, welcome to the Unit 3. Uh, this is actually going to be the lecture for magnetism matter, the fifth chapter of Unit 3, magnetic effect and current, or magnetic effects of current and magnetism. So, actually, we got disrupted in the last class where I was talking about the moving coil galvanometer. So I'll quickly just go through those slides again, and then we will start with the fifth chapter. Okay, so galvanometer, as we have seen, it's used to measure current. Okay, and see whether the current is flowing through a certain part of the circuit or not. So we learned that the principle that is there behind a moving coil galvanometer. Okay, just yeah, it's okay. Okay, so that is actually the torque. Okay, so that is produced due to the existence of both magnetic field and electric field. Okay, but the deflection. Okay, that the deflection that is shown by the arrow. Okay, by this pointer over here. Okay, on the scale, that is actually the it is the function of this phi, okay, which is a deflection. Okay, we can also call it the angular deflection. Okay, so that is dependent on the number of turns of the coil, okay, that we are using for the galvanometer. Okay, then you have the A and B. Okay, so what is A and B? That is actually the area. Okay, okay. So that is what the deflection is going to be dependent on that, and also the current. Okay, so the constants, or actually the terms that are put in the bracket, okay, these are constant for any given galvanometer. Okay, so these are only dependent on if they will vary with respect to the galvanometer that you're using. We will see that galvanometer itself can be used as two different devices. Okay, and the way that they work is actually function of what we have seen before as resistance in resistors put in combination. Okay, so you can have the galvanometer working as an ammeter. Okay, when it is connected in parallel. Okay, small resistance. Okay, this is called a shunt resistance. Okay, why do we need a shunt resistance is that since galvanometer itself is a very sensitive instrument. Okay, so as when the current changes, as per the change in the current, it will show full scale deflection. Okay, and also for measuring current, the galvanometer itself has to be connected in series. Okay, with respect to the circuit that we have seen. Okay, and galvanometer itself has a very large resistance. Now, if it is connected in series, as we have seen, in series, the equivalent resistance is actually the sum. Okay, so as and when if there are large resistors put in combination, it is going to give you a larger resistance, the equivalent resistance. Now if your resistance is much larger, then passage of current is going to be difficult. Okay, so to overcome these issues, we will put a smaller resistance, that is called the shunt resistance, okay, in parallel with the galvanometer coil. Okay, so this is the entire ammeter setup. Okay, this is the entire ammeter setup. This entire ammeter is connected in series. Okay, when we are trying to measure the current using this ammeter. So you can see that the equivalent resistance, you can be the resistance of the arrangement will be given as Rg Rs divided by, okay, I'll just write it here, Rg Rs upon Rg plus Rs. Okay, so Rs is a shunt resistance and Rg is much larger than the shunt resistance. Okay, now we'll get the equivalent, this is equivalent. Okay, so this is what we will get. Okay, to read off the value of the current that is passing through this. Okay, so with respect to the equivalent resistance that we get, we can get the deflection on the ammeter scale. Okay, to understand how much current is actually passing through. Now, to reduce the current sensitivity of the galvanometer, okay, due to the the current that is passing, you can write phi by I is equals to NAB by K. Okay, over here you can see that if you increase any of these, values, you will get an increased current sensitivity. So usually the only the variable that actually controls this entire thing is the n. Okay, n is the number of turns. Okay, so to increase the sensitivity of the galvanometer, we can increase the number of turns n. Similarly, as we have said, the galvanometer can also be used as voltmeter. Okay, so for it to be used as the voltmeter, it has to be connected in parallel with the circuit. Okay, and it because we are trying to measure the voltage across the circuit, we have to ensure that small amount of current is actually being drawn by the galvanometer, and rest of the current is actually flowing through the other part of the circuit. Okay, so to ensure that, we have to connect a larger resistance, okay, a larger resistance resistor in series with the galvanometer. Okay, so over here, your R equivalent is going to be Rg plus R, where your R is very, very large. Okay, so then what we will get, that the equivalent resistance is actually going to be very high and very small amount of current can pass through. Okay, now again, the scale of the voltmeter can be calibrated in a way that you can get the voltage value, okay, of the circuit. So you can also find the voltage sensitivity of a galvanometer similarly as we found for the, um, as we found for the ammeter. Okay, so you divide this area by V, and also sorry, the left hand side with V, and then you divide the right hand side by V. Okay, so what you are left is I by V will give you I by R. Okay, so this is how you can get the voltage sensitivity. So if you increase the current, if you increase the current sensitivity, it does not necessarily, just translate to the fact that even the voltage sensitivity will increase. We can, reduce this by say that we increase the number of turns, like we double it. Okay. So then the current sensitivity will be, the new current sensitivity will be twice the current sensitivity of when we were using only n number of turns. Okay, now we can say that the current sensitivity doubles. But if the resistance of galvanometer will then also increase. Okay, if we increase the number of turns, then your resistance of the galvanometer itself will change, because again we know that that R is proportional to L. Okay, so L will increase if we increase N over here. Okay, so then your resistance will also increase. So if your resistance increases, okay, we saw that the phi by V is is also a function of the resistance. Okay, if resistance increases, then obviously your voltage sensitivity will also will actually decrease in that sense. So if you have n is equals to 2n, and then your R becomes 2R, okay, so the voltage sensitivity will be actually it will remain the same. Okay, so this will not change over here. Okay, so this would become, because over here you will have 2n. Okay, if we write phi by V, okay, just use the eraser ones. So if we use 2n, okay, so as we know, phi by V is equals to 2 n A B I K Okay, so if we have increased the number of turns, we have increased the resistance also by that many, that much amount. So your 2 and 2 gets cancelled. Then your new 5 V remains the same. Okay, so if this is the same. So your voltage sensitivity does not vary with respect to the increasing of your number of turns of the galvanometer coil. Okay, so we to convert galvanometer into ammeter will be different than converting it into a voltmeter. This is the reason. Okay, because current sensitivity differs as well as while the voltage sensitivity does not change. Okay, so with this we finish the fourth chapter. Now we will move on to the fifth chapter. So that is your magnetism and matter. Okay, so till now we have talked about how first of all magnetic field is affecting moving charges and any current carrying conductor. Okay, so again, repeating the principle that it is only when charges are moving that a magnetic field is going to be produced, or due to the passage of current through a conductor is going to produce a magnetic field. Okay, so and also before in the previous chapter we saw that material inherently has a magnetic moment, okay, due to the circular orbit of the electrons. Okay, the electrons actually moving in a circular orbit, and because of the circular orbital motion, okay, it kind of forms a it's similar to a current carrying loop. Okay, so it can be analogous to that, and then it will act as a magnetic dipole. And since if it is acting as a magnetic dipole, okay, because there is a charge associated with either an electron or a proton per se, okay, so it can act as a magnetic dipole, and because of that there will be an inherent magnetic moment, and that itself gives the inherent property of magnetism to a material. Okay, so magnetism, uh, first of all, that magnetism existed has been known for, quite, I can say millennia. Okay, so since 600 BC, okay, so there was a material that had magnetic effect. This was known. Okay, and later on with experiments and seeing the kind of the properties that iron showed, people became more and more interested in understanding what is this phenomena. Okay, so with that, like obviously there have been a lot of uh, scientists, and before that when there were philosophers, and also people understood that there was something which was heavy. Okay, so for there was that was actually the ore of iron magnetite. Okay, so people realized that this material had magnetic properties. Okay, so that is how then everybody started understanding the magnetism, and also then magnetic needles came in place, and then we started getting using compasses, where we were using the earth's magnetic field itself for navigation in ships. And then later on, we also deduced the magnetic polarity reversals. Okay, when people were trying to understand how sea flow spreading was happening. Okay, so all of these kind of scientific advances helped us in understanding magnetism as a phenomena, and the different kind of associations with it. So some very common known ideas that we have for magnetism is that first of all that the earth itself is like a magnet. Okay, and it has, as we know, that suppose this is your earth. Okay, and it has a tilted axis, and this is your north and south. So what we say is that the magnetic field, okay, so the earth itself acts like a magnet, and the field is directed. Okay, the magnetic field is pointing, geographic south to north. Okay, so this is your magnetic field direction for the Earth. Okay, this is your Earth's magnetic field. Okay, now and we also know that if suppose this is your magnetic field and we are suspending a bar magnet. Okay, anywhere, this is at any, we have freely suspended a bar magnet, okay, over here. And what happens is the bar magnet itself, turns and tries to point and align itself in the Earth's magnetic field, okay. So suppose this is suspended, so this will try to act as the north and this is the south, okay. This will be in line with the Earth's magnetic field. Okay, over here, don't get confused with the EMF. Okay, this means the Earth's magnetic field. Okay, now since this is what we have seen. Now, if you get two bar magnets, okay, if we have two bar magnets placed next to each other, okay, you try to bring them near each other. If your north is pointing north, okay, or say south is pointing or south is next to the south the southern pole or the south pole of the magnet, this is going to experience a repulsive force. Okay, similarly how we had like charges and like charges repel, unlike charges attract. So the similar kind of phenomena is seen for bar magnets. Okay, that is kind of a property that we use in a lot of different devices. Okay, so if you bring north and south poles next to each other, they are going to attract each other. Okay, so this is similar to how you have like and unlike charges that we had seen in electrostatics. Okay, this has a similar relationship. Okay, so and the biggest difference now over here that this is similar to how charges act now, but there is a huge difference how sometimes we can sorry, this is so you have two different charges. Okay, they can be next to each other and then they can form a dipole. Okay, so this is an electric dipole. Okay, but in case of magnets, okay, this itself can, if you increase the distance, okay, that is there, if your R is increased, this can exist as two different monopoles also. Okay, sorry, this will be minus. Okay, so these two can exist at like far away from each other. If you place them, they can exist as individual charges, but that is not the case for the bar magnet. Okay, so sorry, yeah, if this is your initial bar magnet, okay, so you have your south pole and you have your north pole. Okay, if you break it in the middle, it will not become just a south pole and a north pole. Okay, so the area or the the section where you have broken it apart, that itself becomes new poles. Okay, they will become, since this side is already north, then this will become your south, and since this is already south, this part of the piece will become north. Okay, so this is what we can say, that you cannot isolate the magnet into monopoles. Okay, like south pole alone and north pole alone. Okay, so that is one of the important differences between electrostatics and magnetism. Okay, we will get two similar bar magnets, and usually, the properties that are associated with this bigger magnet will become weaker. Okay, and the the material that is mostly used, or is inherently magnetic and has a very strong magnetic nature is iron. Okay, and its alloys also have magnetic properties. Okay, so now we see that this is say a bar magnet. Okay, so to understand the kind of what is the nature of the magnetic field and the field lines. Okay, so we can kind of imagine a bar magnet, okay, as kind of a solenoid. Okay, over here you can see that the this is your bar magnet. Okay, this is your bar magnet. Your B is a finite solenoid, okay, which is carrying a current I. which is carrying a current I. Okay, and C is your electric dipole. Okay, so this way we can understand the uh, kind of similarities and dissimilarities. Okay, so how do we understand the magnetic fields that are passing through each of these material? Okay, remember we had seen that if you hold a paper which has a lot of finely fine iron filings, okay, and you bring a magnet towards it, they will arrange themselves in a concentric circle, okay, and those concentric circles kind of give you an idea about the magnetic field, the how they appear and how they are flowing, the magnetic field lines. Okay, so the magnetic field lines are actually visual and intuitive. Okay, so these are not like you cannot see them in reality, but this is how we how people have how people have deduced that this is how they must be existing. So some of the important properties that are associated with magnetic field lines of a bar magnet, or over here, since if we can consider solenoids also, that they form closed loops. Okay, so like over here, this one over here is looking like it's not ending, but actually this will join here and this will become a loop. Okay, so these are finite loops, but that is not the case when we consider an electric dipole. Even for solenoid, you can see that there are closed loops. Okay, but for electric dipole, they only move from the positive charge to the negative charge. Okay, you can see over here. Okay, so over here from the positive charge, they will start flowing out. Okay, but for at very large distances from the you know uh, from here to, say, if you go to infinity, they will not join, okay, anymore. So you can have very kind of infinite the infinite loops. Okay, not loops per se, but you can have field lines which do not meet and will not complete the entire loop of the field line. Okay, and so they can go to infinity also, because they start from the positive side and then positive charge and then go to negative charge. Okay, and then for a magnetic field, we have to see that the tangent to the field line at any given point, okay, it represents the direction of the net magnetic field at that point. Okay, so suppose this is your magnetic field loop. Okay, if you take this point and you draw a tangent, so this is going to be your net magnetic field at that point. Okay, so you can have so suppose this is a point, okay, and this is your net magnetic field. Okay, so you can have you can dissolve it into two components. It's in that sense. Okay, so this tangent is the net magnetic field at every point on the field line that is given. Okay, so the other property that we see about the magnetic field lines is the larger the number of the field lines, okay, crossing per unit area, stronger is the magnitude of the magnetic field B. Okay, so over here in A, you can see that B is larger in region 2 than in region 1. Okay, because a larger number of field lines are crossing in, say this region where, you will have marked N. Okay, but if you take an arbitrary region, little far away from the from the bar magnet, you can see that the number of field lines crossing through this area is lower. So your B is going to be lower. But over here in this region, okay, so your B is going to be more. And similarly for solenoid also, you can see this. Okay, for solenoid also, this is similar, that the number of field lines crossing through region 2 is more than region 1. Okay, then we can say that the magnetic field lines, okay, do not intersect. Okay, this is similar to the field lines that we see in electric field also. Okay, so they do not intersect each other. Okay, because if they did, then we would not have a unique, direction of the magnetic field at that point of intersection. Okay, but we know that the magnetic field has a unique direction at any point when when you take a particular point, on the field line. So now we will see that if how what would be the field, okay, if we consider a bar magnet as an equivalent solenoid. Okay, so we are considering this you can see in the diagram over here. Okay, so we are going to understand this axial field. Okay, the field along the axis of this finite solenoid. Okay, and if this is a solenoid. Okay, so we are going to try to find the say axial, okay, along the axis of this solenoid, and we will try to see that this is similar to a bar magnet also. Okay, so the field, the magnetic field that we get for the along the axis of solenoid is going to be similar to the field of the bar magnet. Bar magnet, the magnetic field. Okay, so we are going to consider a current loop which has a dipole moment m. Okay, so m is equals to n I a. Okay, where n is the number of turns in the loop and I is the current and A is the area. So before we understand, as we said, that a bar magnet cannot exist as monopoles. Okay, so even if you cut a bar magnet in half, okay, so suppose this is your, bar magnet. Okay, if you cut it into half, okay, it can this part A and this part B. Okay, so A and B will also, cutting this will kind of, act in a similar way how we cut solenoids, and then they will not become two, halves of the solenoid, but they themselves will act as a solenoid each. Okay, so you will then get a solenoid of A, and then you will get a solenoid of B. Okay, but they will have weaker properties, magnetic power, but they themselves will be two different solenoids. Okay, and again the field lines will remain continuous, emerging from one face of the solenoid. Okay, um, and trying to enter from the other face. Okay, so this is what we see. Now we are going to consider that this is a solenoid, okay, which has n, that the n turns per unit length, and the length we are considering as 2l, okay, and the radius is going to be a. Now we have to try to see the actual field at point P, okay, over here as you can see. Over here you can see that the field that is direction is marked, which is going through the plane, okay, that is why we have an x over here at P. Okay, and it is situated at a distance r from the center of the solenoid. Okay, and now we are going to consider a circular current element. Okay, over here it's like a disk dx. Okay, and this dx is at a distance x from the center of the solenoid. So now the entire the total number of turns that are there, okay, for this element, for the x current element, okay, we have number of turns as n dx. Okay, n dx. So now if we know that, okay, what would be the magnitude of the field at point P due to this circular current element? Okay, that we can write as dB. Okay, since we are considering a current element of dx. Okay, so that is mu 0. Yeah, okay. So this is going to be mu 0 n dx I a square, okay, 2 r minus x, okay, the whole square over here, okay, plus a square. This is actually under a cube root. Okay, so this is what we get. Okay, we had seen this in previous chapter. How do we get magnitude of the field at any point due to a circular current loop? Okay, so we can just put the values in those, and then we can get this. Okay, now if we are considering the total field, now we want to find the total field. How do we find the total field? Okay, so the total field will then become, there is less space over here, but I'll put it in a better way when I will give the notes. Okay, so this will be B is equals to mu 0 n I a square. Okay, so now we are integrating it from minus L to plus L. Okay, so we will get the common terms out. Okay, and then we can integrate it as minus L. Okay, to L. And now we will integrate the terms that are related. So that is dx r minus x the whole square plus a square and the entire thing under cube root. Okay, so this is what we get. Now if we consider a far axial field, okay, so that means your r is much greater than a, as well as the r is much greater than L. Okay, so the point P is actually, far away from the, the center of the solenoid. Okay, if we consider that, what we are remaining with, the denominator, if you see, then becomes r minus x square plus a square, okay, a by 2 will simply become r cube. Okay, and with that, your b is equals to mu 0 n I a square to r cube. Okay, and now you will only need to integrate with respect to the dx. Okay, now if we also now after integration with respect to dx, what we uh, are left with is b is equals to mu 0 n I, okay, upon 2. Okay, over here we will get 2l a square by r cube. Okay, you can see that over here, okay, so your b finally, just, okay, so your b is equals to, or it is related to the length. Okay, so the length of the, since the total length is 2l, okay, so 2l total length, okay, then a square, that is your radius of the solenoid, upon r cube. R cube, r is the distance from the center to any point that we are saying on the axis, okay, on the axis of the bar magnet. Okay, so this is what we get. Now the magnitude of magnetic moment of solenoid that we have already seen is that, I will just write this properly here, is m is equals to n to l I pi, sorry, I pi a square. Okay, this is your area. Okay, and 12 is your total number of turns. Okay, so this is actually of the form NIA. Okay, so this is the magnetic moment of the solenoid. Over here you are seeing total number of turns in the current in the cross-sectional area. So your equation that we found out before reduces to mu 0 by 4 pi 2 m by r cube. M is your magnetic moment. Okay, so we can say that the the magnetic field of a bar magnet, okay, is similar to the magnetic field that we would get when a solenoid is considered. Okay, so this is your far axial magnetic field of a bar magnet. Okay, far axial field of bar magnet. Okay, so this is what you get. So we can say that a bar magnet and a solenoid produces similar magnetic fields. Okay, now we will see what would be the dipole in a uniform magnetic field. So we found out the magnetic field that is associated with the bar magnet. Now we will see the dipole. Okay, So we will consider magnetic compass needle. Okay, compass needle. You can see that one point one tip of it is north and the other tip of it is south. Okay, north south. You have that. Okay, and there is a moment of inertia associated with this magnetic this compass needle, as well as a magnetic moment. Okay, moment of inertia, and so your moment of inertia is sorry, your magnetic moment is m, and your moment of inertia is I. Okay, and we will see as you have seen that when you hold a compass, the needle actually oscillates along its uh, it will oscillate, okay, and pivot with respect to a center of the compass of the needle. Okay, so obviously we had seen even in the previous class, there's force associated, okay, due to either the field as well as the electric current if you're considering a loop. Okay, so there is going to be torque on the needle. So that torque is given by your tau is equals to m cross b. Okay, and magnitude, since this is a cross product, what we get is tau mb sine theta. Okay, where your tau is your restoring torque. Okay, and theta is the angle between m and b. Okay, so it is the angle between the magnetic moment, sorry, and the field. Okay, theta is due to theta is the angle between that. Okay, so if we are considering the compass to be in equilibrium, okay, so that there is no, deflection, it is in equilibrium, and the torque is, the forces acting on the two ends of the needle is the same. What we get is I, this is the moment of inertia, okay, d square theta by d2, the dt square is equals to minus mb sine theta. Okay, so the negative sign, okay, so the negative sign that we see over here is actually because the restoring, okay, so negative sign denotes that the restoring torque, okay, is in the opposite direction to deflecting torque. Okay, the negative sign, it denotes that this restoring torque, okay, that we see over here, tau is the restoring torque, okay. So that is actually in the opposite direction to the deflecting torque, okay. So then you can reduce this equation into this d square theta by dt square is equals to minus m d moment of inertia and theta. We are considering sine theta almost equal to theta if we consider theta to be very, very small, okay, very, very small and in radians. Okay, then we can consider sine theta as theta itself. Okay, so this is the equation we can reduce it down to. Okay, so this actually represents a simple harmonic motion, as we have said that the compass needle will oscillate, okay, about its center. Okay, so the square of the angular frequency will then be given as omega square is equal to mb by inertia, the moment of inertia. Okay, and then with respect to the angular frequency, there is going to be a time period. So the time period can be given as 2 pi, the moment of inertia by mb. Okay, and therefore your magnetic field associated with that will be 4 pi square upon m p square upon uh, I. Okay, this is the moment of inertia. Okay, so this is how we can correlate the moment of inertia and the time period of the oscillation, okay, of the compass needle with respect to the magnetic field. Okay, we can also get another term, that is a magnetic potential energy, similar to how we have got electrostatic potential energy when we were considering we were seeing in unit 1. Okay, so how is that given? You have that is a magnetic potential energy, that is actually the summation of the or you can, we are using integral over here, okay? The torque with respect to the angle between M and B. Okay, so this is the integral function of that. Now, if you put in the, substitute the values of tau MB sine theta d theta. Okay, so that is going to be equal to MB cos theta. Okay, and now if we have cos theta, then we can say that the magnetic potential energy is actually a dot product. Okay, dot product of the magnetic moment and the magnetic field. Okay, so if we are considering uh, theta is equals to 90 degrees, okay, your UM will become 0. Okay, if we consider this, if theta is equals to 90 degrees, it will become, the potential energy will be 0. Okay, so what does this indicate? That the needle is perpendicular to the field. Okay, so that is your UM is going to be uh, mm, uh, energy is going to be minimum. Okay, so this is going to be, sorry, this is going to be 0. Okay, when needle is perpendicular to B. Now, if we consider your theta as equals to 0, okay, if your theta is 0, okay, then your UM is going to be minus M dot B. Okay, if it is minus, actually, it will not be uh, dot. Okay, since we are considering cos theta, okay, this is going to be product of the magnetic moment and the magnetic field. Okay, but this, since it's negative, it's going to be the minimum. Okay, and for maximum, we have to consider theta as 180, where your potential energy is going to be theta, sorry, it's going to be maximum. Okay, again, this is going to be dot, this is going to be just the product of, the magnetic moment and the magnetic field. Okay, this is a stable position, okay, most stable position. Okay, while if we have theta as 180 degrees, it is going to be the most this is most unstable position. Okay, so we have to remember that if theta is equal to 0, it is the most stable position, whereas if you have theta is equal to 180 degrees, it's going to be the most unstable position. Okay, and if your theta is equal to 90 degrees, okay, that is when the needle is perpendicular to B, your magnetic potential is going to be 0. Okay, so this is what we see when we are considering a dipole in, and because over here, as we have seen, a magnetic, a bar magnet can only exist as a dipole. Okay, so if we keep it in an already existing uniform field, this there is a torque that it is going to experience, and with respect to the torque, okay, you can find the magnetic field, and that is dependent on the moment of inertia also associated with this compass needle. And with the torque that is there, that is being produced, that we have found out, we can also find the magnetic potential energy, okay, as the deflection of the needle keeps changing, okay, at any kind of angular relation between the magnetic moment of the needle and the uh, uniform magnetic field. Okay, so now we will see that we have seen a bar magnet is similar to solenoid. Okay, a bar magnet is also, it can act as a dipole, where it can be related with the electric dipole. Okay, the relationship with that. Now we will see what if we, replace the components that is used to identify the magnetic